Hello, how to prove that a function is continuous and how to prove that a function can be extended by continuity. This is what we'll be doing in this video. So first, let's recall the definition of a continuous function. A function f defined on a domain df included in R2 into R is continuous at a point a1, a2 of the domain if and only if the limit of the function f of xy at the point a1, a2 exists and is equal to f of a1, a2. So this is the condition. This is what you need to prove to prove that a function is continuous. So let's take an example and we'll illustrate the method on the example. Let's take, for instance, the function f of xy equals x2 minus y2 over x2 plus y2 when xy is not equal to 0, 0. And this function will be equal to 1 when xy is equal to 0, 0. So we can see clearly that this function is continuous everywhere except maybe at 0, 0. Because everywhere else it's a polynomial form with a rational expression, so it's continuous. That's why we need to study the continuity at the problematic point, which is in this case 0, 0. So first, according to the definition, we need to study the limit of this function at the point 0, 0. To study the limit, I invite you to look at the previous video where I explain in details what's the procedure to study the limit of a function of two variables. So according to this video, you will start by finding the limit in some directions. So if you try to find the limit in one direction and you find that the limit is in this one direction is not equal to f of 0, 0, which is 1 in this case, then you would say immediately that the function f is not continuous at the point 0, 0. In fact, if in one direction you don't find the limit that we are looking for, which should be equal to f of a1, a2, then no need to find other limits in other directions, or no need to find if the limit exists or not, because even if it exists, it will not be equal to f of a1, a2, in this case f of 0, 0, which is 1. Now let's say that the limit exists, but it's not equal to f of 0, 0, which is 1. In this case also you will say that the function f is not continuous because you are not satisfying the definition that says that the limit should exist and be equal to f of a1, a2, in this case f of 0, 0. Finally, if the limit exists and is equal to f of 0, 0, which is 1, then it's the only case where we can say that the function f is continuous at the point 0, 0. So what about the example we gave? F of xy equals x2 minus y2 over x2 plus y2. So if you calculate the limit, let's say in one direction, which is the direction of y equals to 0, the limit will be 1. So that's equal to f of 0, 0. So let's go further. Let's try another direction. Of course, if we find another direction with another limit, then the limit does not exist and the function is not continuous. So let's try, for instance, the direction x equals 0. In the direction x equals 0, the limit will be, the function will be anyway, minus y squared over y squared. So the limit will be minus 1, which is not equal to 1. So the function f is not continuous at the point 0, 0. Now, how to prove that a function is extendable by continuity at a point, or in French, prolongeable par continuité. So to prove that a function f defined on a domain I deprived of the point x0, y0, so in this case the point x0, y0 should not be in the domain. So to prove that it's extendable by continuity at this point x0, y0, we need to prove that the limit of the function about x0, y0 exists. If this limit exists and is equal to L, let's say, then we can define the extension by continuity as this new function that I would call g in this case, such that g of xy is equal to f of xy when xy is not equal to the problematic point x0, y0, and g of xy equals to the limit I found L when xy is equal to x0, y0. In this case, this point L will fill the hole in the function f. The function f was not defined at the point x0, y0, but it was defined everywhere around it. So the point L that we added to this function allowed the function g to go over this point x0, y0 while being continuous as well.